Great.
So for everybody that is here right now, we're the university and college students out of the group here. So for us, our sessions here are going to be a lot less formal, less structured than the K through 12 sessions. So we're going to be more kind of focused on what you guys are interested in doing and how we can help facilitate that using our platform. So I guess really how I kind of want to, since we're going with that sort of pace, I think it'd be really great if we could try to get some like questions. We have other people join. If we can get some questions from all of you guys about what you're wondering, timelines, different resources that we can help you find. Start there. You can either send them in the chat or you can feel free to unmute yourself too. I think you should be able to do that.
Hi, can you hear me?
Yes.
Okay, hi. You know, since this is Vincent Pereira, since we'll be going about 100 kilometers up, I was thinking of designing an experiment to measure the number using a Geiger counter to record the number of electrons as we go up 50 kilometers all the way up to 100 kilometers and check those whatever data that we have with the current Chapman theory. So is that something that we can do?
Is that something that you were looking to develop your own custom sensors for, or is that you're looking for us?
No. I think the Geiger tube is something that we can get easily. Okay, but the point is that when we design this experiment, we a little bit have got to have knowledge of the maximum acceleration, you know, to make sure that the sensors will withstand the launch. And also we want to know like how would you put the sensors? I mean, like, you know, will the payload doors be open at any stage? Could you have those details for us?
So I think, so the first thing I should say, I'm probably going to pass a question along to one of the other two hosts here. But the first thing I will say is that this test flight is going to be the first instance of this full scale motor actually propelling their vehicle. So I think there is a few discrepancies, and there's the expected acceleration, of course, but in terms of the actual to the T number, it is going to be somewhat difficult to get an exact for you in this situation. Okay. But I'm sure one of these two can absolutely help answer a little bit more of your question there. And then I can also, of course, I don't know if you're in the Discord, but we do have a couple of the Blueshift engineers, and I believe Seth Lockman, the communications director, is also in there too. So we can definitely reach out to them too to get a better estimate.
Okay.
But, is there anything you want to say about that?
Cody, what I'd like to do is I'd actually like to just contextualize the session first, if that's okay, before we jump like all the way into the weeds of it. Great. So as an introduction, I'm Judy Sandrock. We also have Bjarke Gottfredson with us. Bjarke, if you wouldn't mind, just waving. And then these sessions are going to be hosted and facilitated by Cody Harris from the MaxIQ team. So everybody who's here is part of a group that has signed up for this project that we're doing, which is the suborbital launch challenge. We are very lucky. We have the opportunity of flying on a Blueshift rocket on one of their test launches, one of their suborbital test launches. So yes, what it is it's an inaugural project for everyone who's here. So that is really the context of the challenge. We did have a slide. We had a slide earlier, and which was outlining the challenge itself. And a number of you I know were in our session earlier, but what I'd like to do is, if it's okay, I would just like to, I'd like to bring up that slide once again. Let me see if I can do this. Oh dear.
Actually, I have it
Sorry.
right here. Don't worry about it. I have it right here.
You do. If you don't mind, Cody, that would be great. You know which side I'm talking about, only the one that relates to the challenge itself.
Yeah,
we need to just contextualize it for these sessions. So as Cody said, these sessions are going to be very facilitative, very collaborative. It's not going to be a set agenda for every single one of these sessions. To a large extent, we would like you to drive the agenda, and we would like you to drive the topics. So Cody, let me hand back to you to take everybody through, just for us all to remember what the challenge is. Yeah.
Sure. So first, we have two things. First, we have from Blue Shift the opportunity to actually fly our payloads on a suborbital flight. And second is we have from MaxIQ, which is the actual modular electronics, right? The base for, your experimentation. If you want to use custom sensors and whatnot, this is the platform that you're gonna be building off of, right? So the challenge in itself is to create a unique and insightful experiment that's directly related to the United Nations Sustainable Development Goals. And then again, like I said, using those sensors provided by us, or you customize your own and implement that. Furthermore, too, we want students to develop their own way to receive some preliminary data from their kits, from their sensors, right? So we'd like you to test it in some fashion. We recommend model rockets, weather balloons. I threw a makeshift centrifuge into there too, because anything you guys can think of, right? Your experiment is based off of your design, so you're really going to know the best way to get some of that first sets of data better than we would, right? And the desired outcome, right, is for you guys to answer the question: how would you use this opportunity to develop a space grade satellite payload, or how would you further develop it into an orbital picoset, if you will? And then you guys will take all of that, and we'd like you guys to create a presentation that can be presented during World Space Week, which is in October every year. It's the 11th to the 14th. No, it's the 4th to the 11th. I'm so sorry. The 4th to the 11th. Jeez. And then out of all of those submissions that we're going to get from all of you guys, plus some of the K through 12 students, we're going to choose the top 3. And then for that, we'll sponsor you guys to go on the first orbital flight from Blue Shift Aerospace. So you can either modify your experiment slightly, or you can run the same one. And that's about the challenge right there. This is the only slide you wanted out of this?
Yeah, Cody, that's absolutely perfect. Bianca, I was wondering if you wouldn't mind coming in to answer Vincent's question. I'm not sure if you'd like Vincent to just repeat his question to you in terms of his experiment that he and his team are thinking of.
No, I got it. So that's fine. But I think the important part here is that for those who wasn't here in the earlier session, maybe that's just important, especially if you want to do your own. If you want to do your own sensors. The way it works is that you all have the SDG kit that Judy kind of like have alluded to, and there is a number of different sensors with that kit. What you're getting on a later stage is you're getting another core. So the core that you have with the SDG kit is this one here with 7 touch buttons on, okay? And on the back of that is a ESP32, which have the Wi-Fi, Bluetooth, and 4 MB of memory. The core you're getting is this one, and I apologize a little bit here because I have a green screen, so this one here is a green. So therefore it looks like odd when I show it to you here. But it's actually a core with the same ESP32, and it runs exactly the same software as your normal core. It's just that you configure it to how you want to use it. It also have a SD card slot on it. It have a camera slot, the OV2640 or similar MP CSI camera slot on it. It also have PS RAM that allows you to use the camera in full frame mode. And then I have an extension slot at the end. And you will get this one here like it is here. and then you will get a couple of other things you can use for the extension slot. So the one is just a little board. It's red here, but it's going to be white in the future. And that is maybe a little bit difficult to see. Let me see if I can make a little bit light on it. But you have actually the extension, which is SPI. It's I2C. It's a 3.3 volt and 2 GPIO pins that you can access like that. And then we have a simple one for especially for the high schools and things like that just want to maybe put something together with a simple sensor. So this is like if you have like a, you know, any kind of like a light dependent resistor or any other resistor based sensor, then you can kind of like solder in a resistor that matches that and do the voltage divider, and then you have your own project. If so the way it works is that the software here that is on the core, you can write your own software. There's nothing wrong with that. We will release a framework for the software that have to be there, because the way it's going to work is that when you fly on a Blue Shift rocket, you will get provided power, and you will get around 250 to 300 milliamp. So if you want to do use a Geiger Counter module, they're like I think they're like 300 or 400 volts things. So you have to up the 3.3 volts to that, and I'm not sure how much juice you need for that, but that could be the first limitation. Each of these projects, you will typically for most of the students, you will use the same sensor you used in the other, and you will just click them in, and then you have a 10 by 10 centimeter payload. So that's your other limitation. You have to use this core, and then you have you can design your own PCB here that's 96 by 64 millimeter if you want to do that, and we can kind of like send you like a layout, and then you can kind of like design itself. The communication platform you have is I2C, and to a certain degree you also have a serial connection, and you have one GPIO pin you can use. So if you want to use SPI, you have to use the extension port for that. But this is the way, and then the limitation is then that you have 1 centimeter in height. So when you so that could be another problem if you do a Geiger counter, and especially one to point it sideways. I also don't know with the rocket right now. We probably have a window, but otherwise the rocket is sealed off because it's going to land in water, and you want to have the whole thing coming back dry. So there's no access to space, if I can say that. You will be inside a rocket, which hopefully have some sort of window that you can use for light sensitive sensors, or maybe even the camera. And then so you will have 10 by 10 centimeter like I have here, but the 32 is already booked. So you have 64 by 94, and then you have 1 centimeter in height. And the reason for that is that once for each of the universities or schools, institutions that participate, they then be loaded in a 3U, in a 3U. So this is 30 centimeters, a 3U long, and they have this kind of connector at the end here, and there's one for each centimeter. I only populated the 3 of them because this is just a prototype to test it. But for each centimeter, there is one of those, each 10 millimeter, and then that be slided in like this in the project. And I'm just gonna take another one that I'm putting in a little bit higher up. I call this the spine, and the core we call a vertebra. Probably that could be a better name, but that's what they're called now. So you can imagine how this is, and then you have this, and this is exactly from the outside to the outside of this spine here is 10 centimeter, 100 millimeter exactly. So this is kind of like the 3U satellites that have been launched in with 30 of these platforms. A couple of them are used. So the way it works is that your platform is communicating with a mothership that's sitting at the bottom of the top of this thing here, and that you communicate with that using CAN, the CAN bus. So there's a CAN bus on this thing, this core here, and then we have a motherboard on the bottom that then pull every of the different projects using CAN bus, and we get the data. And the data is in message pack format, which is kind of like a very compressed version of JSON, if I can use that. It's called message pack. If you use that doing a JSON, it's kind of like built into that also. And that's a very compressed format. And that we take, and then we download it using the Blueshift radio link that they provide. We're not sure what kind of radio link they provide yet, but you don't have to be concerned about that, because you're just getting the data pulled by a CAN bus, and we then have a motherboard that then distributes. So we will pull each of the payloads for data. The Vertebra here, the core you're getting, also have an SD card, and there the data will be stored in a much more reader-friendly format. So you can, when you receive your Vertebra back, or your payload back, you can take the SD card and download the data. The reason why we use the radio to download data is that, hey, it's a rocket in space. You know, we don't know if they actually are safe in recovering the payload out from the water. So just for good order, we're going to download as much data we can on that flight. We are also planning to use the same technology to send stuff to the International Space Station. And it's the same thing. There's some power that might be completely different. I think they provide 28 volt plus minus. And there's some other data communication there. So we provide a 3U there that can go there. We've done it before without the communication, just the power. And then the SD card, because on the International Space Station, you can typically get your payload back after a month in space. So they're slightly different. And that's going to use the same kind of philosophy. So same kind of like, you know, obviously maybe different sensors, because there's no window. You're typically inside a sealed off box. There's also, with the Vertebra, we also released a LoRa radio. So here's a radio that slots into this extension port on the board here. The LoRa radio that we provide is a 433 megahertz, which is the one that gives us the best coverage. It's a license-free in Europe and Africa in ITU region 1, and in the Americas you need to have a radio amateur license to use it, but most universities are fine with that. It's very low power radio. The LoRa's benefit is the very high sensitivity. So the 168 dB link budget means that you can actually, we have successfully communicated over 200 miles apart from a balloon and a ground station using these radios. There's also some project, tinygs.com, which is like existing satellites that fly in space using LoRa. You can build a ground station using this board here and a better antenna, and then you can actually set up a ground station and listen to existing satellites that's out there. There's the whole project listed on tinygs.com. So that's kind of like how it is. As I mentioned, you can put a camera on it if you want to. There's an SD card if you want to put that on. The different slots are for that. We provide this one here, plus a couple of these boards that I mentioned before that you can prototype with. And then you, of course, have all the sensors. And then later, you're also getting a AA battery, a power module at the same time you get this thing here. And hopefully in later states, we might provide a power module that uses a LiPo battery, rechargeable LiPo battery. But for now, it comes with just a normal AA battery that helps you fly in in a in a model rocket or even a balloon project if you want to do that. So just to round it off, Vincent, I think you asked if you know, if you could do a Geiger counter. As I mentioned, you have 1 centimeter minus the 1.6 millimeter you have to use for the PCB. So you have very little space in height for a Geiger counter, and also I believe it uses quite a lot of power. I never built one, but when I looked at it some years ago for the SynSat program, it seems to be something that needed a bit of juice. So that's so what we try to do with this first flight here is make sure that you can do some simple sensors like I asked here SPI sensors, or even maybe just build something for the purpose of kind of like have a educational experiments with this thing here. So like you know, either like an analog sensor like that, or you can of course get some, you know, like a breakout board from Adafruit or SparkFun or Microelectronica or whoever you use, and then this breakout board here is a standard 0.1 inch you know, breakout board where you can then click it in. If you choose to just use this thing here, this kind of like analog with like LDR or something like that, then the code that's provided in here will automatically just report the voltage level that comes out from these two sensors on a JSON that's being uploaded. If you choose to kind of like come with your own sensor, then you have to write your own code. But as I say, when you get this thing, have you also release a framework with the code, so you have so you can build your software from there. The framework will not have all the other sensors in the framework, but the code that we are releasing on this one here is also free open source, so you can go in and see how that code is done and steal the code there if you want to. I think I'll give a pause here and let questions and other things come in. Judy, Cody?
That's great.
Yeah, the chat's going right now. We got a couple of questions in the chat that I'll go to. So somebody says, given the current limitations, what sensors are feasible to use in the rocket? And they said so far, you know, it seems the accelerometer and the GPS would definitely be useful. Do you have any other recommendations based off of what we had? I know, like, I think you guys are right. I'm pretty sure that we are going to have a window that's going to be shown. So like the light sensor will definitely have a bit of purpose there, and we also have the we have an STL file for a curvature, a mirrored mount that can go over the light sensor that can kind of angle the light onto the sensor a little bit better too, depending on the orientation of the payload within the payload bay. But Judy, are there any other sensors that you could think of off the top of your head that, you know, might actually be quite useful during this first flight here?
Yeah, Cody, what I'll do is I'll put together a list of the sensors that we can discuss. In fact, I think we did have it on one of the slides, but Dinesh has had his hand up for quite some time.
Oh, I'm so
Dinesh,
sorry.
can we please go to you, and then we're going to pull up the slide of all the sensors that are going to be available.
Sure.
Awesome. Thank you so much, Judy. Good afternoon, everyone. Again, hello, Judy. Hello, Dr. Edmondson. Nice to see you again. Just a little introduction. My name is Dinesh Ramsiwak, and I am the faculty advisor for one of the Caribbean teams, specifically from the University of Trinidad and Tobago. I will make mention, I think we have some students here from another Caribbean team in attendance from the University of Guyana. My questions are two, and they're very simple. Thank you, Cody and Bianca, for the comprehensive introductions. This is being recorded, so that will be very useful for us. But in addition to that, are there any other resources that you can point us to in terms of some background literature on the sensors or the kits, maybe some online videos, anything that can support these students in that regard? That's one. Maybe I can pause there. You can answer that, and then.
Sure. Well, yeah, we have a series of different resources I can reach you guys out to. The first thing I would recommend, though, is everyone should definitely join the Discord page. From there is where I'm really starting to compile a lot of links to everything. And also on the MaxIQ website, I'll send links in the chat here in just a moment. But we have we have links to our GitHub account, which is for anybody who's going to be interested in creating their own custom sensors. You'll definitely find a bunch of useful information there. A lot of it will be actually on our main MaxIQ website though. So I think what the best thing, like I said, is I can recommend is joining the Discord group, and then in the announcements tab on that Discord group, I'm gonna have a whole series there's already a whole series of links there, but I'll keep adding to it, and I'll make sure I'll let you guys know when everything gets updated too, if there's any changes.
Okay.
Yeah, is there anything you're specifically looking for though? I should say too, our YouTube channel, I just got that started, but I think we're gonna start populating that slowly over the next like week or two. It might take a few of our old recordings and whatnot, but it will probably mostly be more dedicated towards the newer content. And then any specific questions that any students have or anybody has, and from there we can take your questions and we can kind of fill it up with the information you're looking for.
Okay,
Cody, are you going to have a Rob Cartwright with Taylor University? Cody, are you going to have like a single web page where you drop all this and it's
Yeah, no, we have the MaxIQ website page. There's a page on there that's already being populated pretty well. I just don't want to get too kind of like jumbled all together, you know what I mean? So I'm gonna have a little bit of organization in there, but I'll definitely make sure that it's easy to go through and you guys can find whatever you're looking for. And again, if there's anything that you can't find, please reach out to us. You know, I mean, you know, it's somewhat difficult to kind of guess what you guys are gonna be looking for in some instances. Right. So we try to put it all together. But if there's anything specific though and you can't find it, please let me know.
Well, I think we're definitely going to be interested in knowing what the arrangement on the rocket's going to be like. I mean, we can do our own model rocket, we can do the hot air balloon, but when we start talking about the real launch, we've launched other satellites, and we just need to know. We've had a lot of things come up, little hiccups. That happens. It's a big project, right? Yeah, knowing like we got mounted the last time behind another assembly, and then that one didn't launch, and then we couldn't get out. And now we're not launching in that way in this launch, but we, you know, like you talk visually about if it's in a closed chamber, if there's the Jork was talking about if there's a window to allow you to see something, or and the temperature issues. I saw another post on the chat, you know, knowing like if we're in this enclosed chamber, can we use any temperature data? One of the things I know we might be thinking about is to do bit flip testing. So when gamma particles hit the memory cell, does it change the bits? Well, we need to know, are we packed inside of something, and thus will we be hit by gamma? And also, will there be other devices, you know, around us and stuff?
Yeah, no, that's absolutely a great question. I think to answer that one, I won't be able to give you the exact answer right now, but I'll definitely reach out to the Blue Shift team too. Sure. And so internally, you know, we can come up and make sure you guys are definitely aware of like what the orientation and the situation is going to be for each of your individual specific payloads.
Yeah.
Cody, I've had my hand up. Sorry, Cody, I've had my hand up. Sorry, Dinesh, if you, I want to also assist with answering that question. On the kit that you received, there's a Blue Shift branded chip. Can you see it? Can you see it here in my camera? Sorry, I don't know if all of you can see my camera.
Yeah.
On the back, there's a QR code. This QR code takes you to one web page that has got all of the content. As we gather the content, we are posting it there with all of the links. Dinesh, I want to come back. I want to come back to your question. Sorry.
I think we did go to it. I'm not sure that it was.
Oh, I think you're still on. Yeah.
Okay. No, sorry. I thought somebody was asking. So, Dinesh, I want to come back to your question in terms of, you know, of the content. Very structured content that we're compiling and distributing to everybody is aimed at the high school level, and that will be delivered in with the K through 12 sessions that we have at 9:30 a.m. on the Wednesdays. What we're doing is that we're making all of the teacher materials available to everybody who wants it. Just request it from us and we will be able to supply that to you. So that, for example, we do have a number of elementary schools who are participating. Their teachers will receive those materials, those teacher guides, so that they can then adjust that for their students. And so you know, just request that from us. And then what you could do is you could also then adjust that for your students, you know, kind of like take it up a number of notches. So that is what we have planned to provide in terms of content to support you. Great. Sorry, I'm now going to keep quiet. quiet and carry on, everyone, with the discussion.
Yeah, I just have
I think the next have another question. Yeah.
Yeah, just one quick thing, and it's kind of related. I'm glad Judy you mentioned that, because as you know, our kits were only shipped yesterday, I think. So we're hoping to get it next week. So my question related to that is, how soon do you think we'll actually need the kits to begin? Is it from the very get-go, or will we be behind the ball?
Unfortunately, your confirmation only came through late last week. So there was literally nothing we could do about getting the kits to you sooner.
Yeah.
There are a number of teams who are booked to participate, but we actually haven't had their confirmations yet. So that is quite challenging for us. You're definitely going to be able to catch up. Really, these kits are the materials we've put together so far for you to get the starter kit up and running. You literally will get the kit up and running within 5 minutes. So you don't need to worry about falling behind or anything. You'll definitely be able to catch up.
And I'll say this too, building these kits, this starter kit that we just sent out, this is the first time I ever even did any of these things, to be honest with you, right? And I had mine up and running in 20 minutes with the dashboard receiving data. So it's very quick, very seamless. And we have a whole bunch of support material for walking you through, getting started, getting linked up to the dashboard, all of that stuff. So, and again, if you have any questions, please reach out to us.
I just also want to add that there was, I think, Vincent, you asked about the D-Force. So Cody, if you recall, I think that in the last session that Sasha said that they will limit the G-Force to 5G. There will of course be some vibrations, things like that, but 5G. And then with regards to current, the sensors, all the sensors we have in this kit that Judy held up, except for one of the sensors, they're all like in a 1-2 milliamp range. There probably a number of them in microamp range. The only one which is not supplied to you, but if you request it, you can get it, is our air quality sensor. I think that runs in 30 milliamp or something like that. But the rest is kind of like very low power. So if you're looking for sensors, typically these I2C digital sensors, they are like super low power. The core that we're using, because we're not using Wi-Fi, Bluetooth, anything like that. Normally, if you use Bluetooth, Wi-Fi, we get up 200 to 300 milliamp. But in this configuration where we just use it as a core, we're running in like 20 milliamp per range and things like that. So there is juice for other stuff. Let's call it for other, let's call it like normal level sensors. But there's not for like necessarily some stuff that really needs a lot, like probably a Geiger counter. But I'm not super familiar with the latest in Geiger counter. There might be something that works differently, that or you might actually be able to use some super caps and things like that, and charge some power up on your own board to fire that off. But I don't know. But that's kind of like the limitation. And also, yes, we have I released a paramedic file for making a mirror for the so your light sensor actually looks sideways, so it looks out the window. I'm probably going to update a little bit, because depending on how big your mirror is, this could easily reach over the 1 centimeter barrier. But there is actually small, you can get like 1 by 1 centimeter windows mirrors from Amazon. So I'm actually going to order them and make sure that it works fine. But the paramedic file I've done should support that. So if there's other stuff, also the camera, that you can get the camera for this thing here, The ones I have are these tiny ones here. So I don't know if you can see them clearly here, but they're these small ones, and you can get them. So they do high definition video, so 1080p. You can get them a much longer flat cable, and then the idea is on a frame that we built for these satellites, there will be a slot to click in the camera, so you can put it on the side. So hopefully it can look out the window and shoot, some pictures that you can then put on your SD card, or maybe in the video if it's fast enough. I also just want to say that we are making software, one standard package software that kind of like is meant to help as many as possible. But the core you're having on this one here, including the PSRAM and the camera, is actually good enough so you can do TensorFlow machine learning style stuff. So you have ample opportunity to code the way more advanced solution that we are providing here. So if you want to kind of like try to see something out the window and try to do inference in the sky, then you have the option to do that also. Yeah.
Awesome.
Other questions?
Thank you very much for answering many of my questions. I just have to confirm what you just said, is that all the sensors will be in a closed area in the rocket, right? So there's, with exception of a window, it is all enclosed. Am I right?
That's correct. Yes,
Okay.
it's on the way it's going to be is that this rocket, unlike when it goes to space, is that this is going up. It's going to have I think 10 minutes of weightlessness or something like that, and it's going to come down and land in the ocean. And for that reason, we try to make sure the water doesn't run into the rocket, both so it keep floating and so it doesn't destroy any internals in the rockets. And then it's going to be recovered and on land, and you get your circuit back. And for that reason, of course, there's no access to open air. But a window is what they have planned to do, and it's the same reason why we don't. We're not going to in this flight here. And all this can change in future flights. Blue Shift is this will be their first flight on that altitude. So and of course it's still suborbital. They haven't never done an orbital flight at that point. We're not doing external antennas of any kind, so that's also important to understand. That I don't mind if you have an antenna on and you hope it can kind of like get through the noise of and through it can pick up something, but I wouldn't guarantee it. You're definitely not going to be able to put an antenna on the outside of the rocket and kind of like link it in. So a window is what there is. I think accelerometer, maybe gyroscope and the magnometer and things like that might be stuff. Light sensor of different versions, hopefully that the window they're building is good enough to let the various kind of radiation going through. So that kind of stuff. Otherwise, maybe something on board the rocket, like for example, temperature and things like that. What's the atmosphere inside the rocket on a flight could be interesting. But the idea with this thing here is actually the learning process of trying different kind of sensors and build something and get it on a rocket and kind of like get the organization going with this thing here, and hopefully be able to use it as a learning platform, a springboard for bigger and better satellite projects.
Yeah, absolutely. That was actually something I was going to say, is that really like this first experience should just be seen as like a rough opportunity of starting to think about what kind of payloads would you want to test once we go fully orbital, right? And then getting down the framework of those things and just trying to try to create the structure for how you're going to move into the future as these flights become more regular, as the electronics are more accessible. And something I was going to suggest too, right, is that since this is going to be the first run of this rocket, maybe what we could do is we could start talking to some of the Blue Shift engineers and seeing, what type of data are you guys looking for, right? So then that way, then some of the students would be able to help facilitate the aerospace companies actually make, real changes to their systems. So I think that would be a really interesting opportunity. And something actually I'd like to suggest to you while we're all here is that Blue Shift Aerospace has their own Discord page as well. I could probably find the link for it and post it on ours, but that might be, a great resource where a lot of you guys have questions that are really specific to the actual launch vehicle. And they have channels within their Discord where you're talking directly either to Sasha, the CEO, or to some of the engineers too. So of course, I don't mind at all middlemaning and, taking your questions and whatnot and asking them and bringing it back to you. But also there are direct communication channels available for some of these questions.
Michael?
Yeah, but Bjarke, I had a question, but also just to chime in on Cody's point just now. Interesting things to sense in the payload bay. You could think about all the different launch vehicles have a user's guide or a mission planner's guide. And so they're all posted online. So you can look up Falcon 9's user's guide and see what sort of data they post about the environment inside the payload bay of a rocket. And for Blue Shift, it's probably, they're working on it, but it's probably largely a blank sheet of paper. So just an interesting engineering exercise is imagine that you're trying to populate that user's guide yourself. And so things like the temperature during ascent, the pressure during ascent, I just imagine that your school's challenge is to write the payload bay user's guide yourself and try to fill out all the gaps that might exist in Blue Shift's user's guide. I mean, presumably they'll be taking all that data themselves, but it's a good exercise to imagine that it's your challenge. My question, Bjarke, I think I missed this, but you said the data will be, that our readout data will be pulled over the CAN bus or downlink by Blue Shift. Is the CAN bus going to be listening, is going to be logging the SD card directly, or is it listening across the serial or I2C lines, or what actually is going to get logged?
Okay, so all the data is going to be logged on the SD card on the rocket itself. So the way the software is written is that right now, if it uses Wi-Fi or if it uses the SD card, it stores all the data. If it uses a slower uplink or downlink, in this case here, either LoRa or the CAN bus, then it's going to be only the raw data, raw being, for example, temperature and humidity, but not like dew point and other calculated values. And they're going to be downloaded using not JSON, but message pack, which is a standard similar to CBOR or some of these other compressed formats. And the way it works is that the ESP32 support CAN directly. So it just have a transceiver, and the way it works is that the motherboard is going to pull each of the different boards and then ask them to provide that message pack, the telegram with the data, and it's going to go to the motherboard and it's going to be uploaded using whatever downlink that's been provided for us. The only thing I know by now is that I can do the CAN bus and I can do the software for collecting the data and message pack and all that kind of stuff. And as we're getting closer to the actual launch, then I can actually start, testing it with Blue Shift and downlinking it with whatever solution they have.
So I guess where I'm going with that is,
yeah,
if we want to populate that packet ourselves with our own, with some other sensor data, or even just change the packet that goes into that log, is there some packet format we have to respect and some data budget?
Yeah, so I'm gonna do a framework piece of software that have that limitation built into it.
So as long
So
as
if you want to,
your array and we put something else, you're going to have some array in there and we can put something else in the array.
yeah, absolutely.
Yeah.
But the way it's going to be is that the way it's going to work is that the first packet is going to be the chip ID of your chip, and then when it comes down, if you're not following the formats that we have in our main software, because you probably wouldn't do it, then when it comes down, I will simply just unpack it and pass it, either give it to you directly, and you can then unpack it yourself. You will see it's if you use Arduino JSON, which is kind of like the #1 JSON tool in Arduino. There's a message pack is also supported there, similar to JSON. So you unpack it with that, and you just use the same structure. So you build up a structure. Obviously, there's going to be some limitation to how much data we can downlink, but this is not FinSet global star stuff with 36 bytes or something like that. So I'm not going to be too difficult about it before I understand what the limitation is from Blueshift. So if Blueshift puts some expand on it and things like that, hallelujah, then we have enough.
Oh.
But if they do if they put a global star chip on it or something like that, then it's going to be horrendous little data we all getting in those 10 minutes. Okay, and then we're definitely going to rely on the SD card. And as I said, on the SD card, I'm just going to put the raw JSON in, so you build it there. But all that, when this is released, that's what I promised to Daniel yesterday. When this is released, there will be the main software that you can just download, and I don't expect you necessarily going to be able to compile it because it uses libraries everywhere. I am documenting it, but there might be modifications to library, or you might use a newer library than the one I downloaded and things like that. But what I'm doing with the framework is that that's going to be logged into very specific versions of libraries and things like that. For example, for Arduino JSON or like the CAN software, it's going to be a local library. So you can take that and then you can build around that. So that's going to be kind of like the minimum software for your downlink. So there will be both an explanation of how much data you can do and things like that. So I will make that in the next 3 weeks. And then you will there will also be the framework where you can see an example of how you can do that. And another thing is also what my idea is to eventually make a test software for the CAN. So if you want to see that it works, then you can install the test software on another one of these ones here, and then kind of like see, okay, it talks together, it's fine, it works, and things like that. So especially if you're going to do your own sensors and things like that, maybe you should get 2 of these cores here.
Jakob, we have a question.
Sorry, just one more thing to hang on, Judy. Just one more thing. If you use the LoRa, it's also going to be the same message pack as I think I mentioned. So and of course, if you do a balloon flight, you need 2 of the LoRa radios and 2 of these, one for ground station, one for flight station. For you, Mark, it goes without saying, but for the rest, they just have to make sure they understand that. So we provide the LoRa as an add-on because that's not necessarily needed for this flight here. Sorry, Judy.
Yeah, Bjarke, I think some is getting a little bit lost in the Danglish also with the accent. Sorry to say. You're referring to the JSON files, and then there was another one that you were referring to. I know you were referring to CAN bus, but there was some other file format you were also referring to.
Yeah, it's called message pack.
Message pack.
Yeah, it's in one word. There's probably like a wiki. Roy, have you found it? Is that okay? You found it. So Taylor University, they know all about message packs. So they're now gonna run a Discord group for message pack. You should never put your finger up there. Anyhow, but that's Judy. That's there's a number of these different kind of like compressed formats. The most famous one is called CBOR. There's like 4 of these different formats. I chose message pack because it's the one that compressed the most. It's kind of like half size from the raw data, and it's one of the things I really liked was it's supported by Arduino JSON, which is a very, very stable and well supported library, which I used already. So therefore, I'm using this thing here. So you should be able to find more about it. It's basically if you look at Arduino JSON and then search in their documentation for message pack, you'll find a lot about it. Definitely the format we should have been using on ThinSet, let me put it that way.
Awesome. Thank you so much. Just so everyone knows too, I just stuck the invite link to the Discord group in the chat below. So for anyone who hasn't joined that, definitely take a moment to hop in there. Do we have any more questions before we wrap it up today? Because we only have the schedule for about an hour. Either in the chat or you can feel free to unmute yourself too if you feel comfortable speaking in front of everyone.
Just a quick question on the modules. Every time I've ever seen a sensor like this, the circuit board is bare, but this has paint over it. I haven't tested it yet. Is it going to work or?
Oh yeah. Oh, it works.
Okay, good.
I've got mine set up right now. I'd go get it, but we're collecting data. I don't want to pull it off the power right now.
You just hooked it up at 9 o'clock. So
perfect. Awesome. Looks great.
Yeah. The soil moisture sensor. Yeah. Yeah. It needs to be calibrated.
Maybe. So the soil moisture sensor is and I can't say this word here, capacitive sensor. Okay. So that's the reason why it actually uses the same technology as the touch sensors here. It's the same piece of code. There's no difference. The nice thing about these ones compared to the one where you see the bare metal, which of course is resistor based. The resistor based is a little bit easier. You put them into ADC and things like that. But it actually when they run creates this slightly electricity, so they kind of like deteriorate very fast. The nice thing about the one you have there is that because it's covered and things like that, it lasts much longer. I put a link to the message pack from Wikipedia in the chat.
I'll say while we're talking about the soil moisture sensor too, I would definitely just make sure you have that planted right up to the line on the, if you can see like the roots of the tree there, make sure it's planted right up to there. Yeah, you can get slightly different data if you're not fully there, but perfect.
Cody, I was just wondering if do you have the slides there? Maybe if you could share the slide of the sensors that everybody has, but also the sensors that we will be providing.
Absolutely.
That'll be great. So we just have that list. When I copied and pasted it, made such a mess in the chat.
That's okay. So, so these are the sensors. This is everything that's included in the starter kits right here that you should have already received or will be receiving shortly. If you want to go through, we have the weather sensor, the light sensor, your soil moisture sensor, processor.
Hang on, sorry, hang on. You're going through it way too fast.
Too fast. I'm sorry.
Way too fast.
I apologize.
Okay, so yeah, the weather sensor is giving you temperature. This particular weather sensor that we have in the starter kit gives you atmospheric temperature and relative humidity. And then the light sensor gives you a natural light intensity in lux and UV index. Yeah, you have the soil moisture sensor, which you're probably not going to fly. You have your processor with your ESP32, your USB power as well as a programming interface. The display is useful, but you're not going to be flying that. And then yes, you have the Blue Shift mechanical chip with the QR code on the back. And then we have 8 of those connectors. Great. Lemieux, I can see that you have a question. Would you like to ask your question now before we go through the rest of the sensors?
Yes, sure.
Great.
It's pertaining to the programming language that we'll be using. So so far on the GitHub repo, I'm seeing here all the libraries are in C++. So I want to know going forward in the module that we're going to get the upgraded version of the ESP32, would that be also in C++ or would we do it in Python or any other language?
So I do the code that I'm providing is all existing libraries for these different sensors. There's kind of like a 5 times bigger chance that the sensors are available in C++ than are in Python. You can program the ESP32 in MicroPython, and actually the software we recommend to use is Co2 which is a IDE where you can actually upload the MicroPython to this thing here, and you can download the software. These comes pre-loaded with firmware on. But if you program them and therefore want to restore this thing here, then Co2 have like a facility where you can then upload this software again. It's the software is available on GitHub where you can download the bin file, so you can upload it to this core here, and it's the same on both of them, same software that runs on both of them. So you can code it with Python, MicroPython. You of course have to I'll find the library somewhere in GitHub, and that's simply just take the sensor name and then see if you can find the sensor name in Python, or you can write your own library. There's data sheets available, and especially if you kind of like understand Python reasonably well, you can probably read off a lot of the sensors, how they're written in C++, and just look at the addresses there and the registers and things like that, and see what you have to do. Some of the sensors are very, very easy. It's kind of like there's no configuration. I think, for example, our sensor that is not listed here, but you're getting in an upgrade kit is a barometric pressure sensor with temperature. It's literally reading 6 bytes from the sensor, and then do a little math on 4 of these 6 bytes, and then you have your value for both pressure and temperature. So that's and you can see the code there. So even if the library, there's no Python library, you can easily either write a library or just include it in your code directly. But we are not with this thing here that we put together here. We're not using any libraries. We're not using Python at all. But it's excellent tool for the ESP32, and is well supported. So I wouldn't hesitate if especially if you want to do something like that. The framework we're giving is going to be a framework that's C++. So you just have to figure out how that is if you want to do your own code in Python also.
Judy, you said in the light sensor it is UV. What wavelength?
So Judy, maybe I should answer that. So the best way of answering that is that I tell you what sensor it is, and then you can actually look it up on the data sheets. But what I rather want to do is that I think Cody is providing a page somewhere where all the sensors and what the underlying sensor that's behind it. So I can't remember on the light sensor what sensor it is. You know, I could look it up and just put in a link here if there's other questions. But there you'll be able to see the wavelengths. Typically with light sensors, UV sensors that don't include UVC, because we don't have UVC here on Earth, that's get absorbed before it comes down to us. And of course, a lot of these sensors are not built for, you know, like a research or satellites use. They're mostly built to plug into a cell phone or something like that, where they're being used in the millions. So the UVC here is typically a broader wavelength of most UVA and half of the UVB spectrum. That's kind of like the standard for these kind of sensors. So if but you can, and it kind of like falls off in of course in both ends, but they will be in the data sheet.
Thank you.
Are there any more questions, or you want to move on to the next chips they'll be receiving, Iris? So with extension to the starter kit, you guys are going to receive a few more things. The first is going to be an accelerometer. Actually, Judy, do you want to walk them through each of these individually and just type of data?
No, I actually, if you like, let Bianca take everybody through.
Even better, right?
Great.
Yeah.
I think you're muted.
Thank you. So the more sensors that's coming here, so there's an accelerometer, and it's a 3 degree of freedom, so it's X, Y, and Z separate. It have like some kind of like tap detection and things like that. So you can you know, use it for tap detecting, double tap detecting. Not that interested in here. You know, we just want to use it either for measuring, you know, the G-force or the vibration and that kind of stuff. But as I said, they're separate for X, Y, and Z. And you can probably, you know, calculate maybe pitch and rollers, things like that, or magnitude of acceleration in general. I think it's a 248. The resolution is 2G, 4G, 8G, and 16G. But I don't think we hit more than 5G, so a resolution of 8G is more enough than for this thing here. Then you get an atmospheric pressure and temperature sensor, so that gives you, you know, the pressure, and there's a calculation built in that gives you an altitude based on a standard sea level, 1013.25 millibar or hectopascal. So it's not an accurate one, but it's you know, we're just using that for giving an indication of altitude, but the pressure sensor is pretty accurate. Then you the third point here is you're able to create your own sensors. So as I mentioned before, the one board that's going to be wide in the future, this one here, have like 4 pins out for SPI. So chip select is one of them. And there's 2 other IO pins. So there's reality 3 pins like that. And then there's I2C, and then there's 3.3 volts and ground, of course. So if you have a sensor that runs 3.3 volts, one of the nice things, a lot of the Adafruit sensors, they make sure they run both 3.3 and 5 volts, even if they are 1 pair 8 volt, then they kind of like have a level shift and things like that for 3.3 volts. So if there's an interesting other sensor you can find like that have a breakout board, you can kind of like soldering into this thing here, and then but again, the software of course have no clue what kind of sensor you plug in, so then you have to go in and write your own software. Then there's the standards, kind of like, as I mentioned, expansion you can do with this board here. I know that Michael Galvin, who is running forward and backwards in front of his screen here, he's school is maybe building a prototype board, and the prototype board is going to be this size here, so 64 by 96 by 64 millimeter, and that's going to be kind of like a bigger prototype board with holes for you can then use the bus connector we have here on the side, and this thing here, this 10-pin connector here, supports I2C, a serial connection. There's a couple of pins for programming the master, and then there's like one pin we have allocated as a GPRO pin that's currently being used for the soil moisture sensor. And yeah, so that's the different pins you will have on this board here. There's no SPI, but there is serial and there's I2C. So if you have something, a bigger project you want to kind of like lay out, we can also share the PCB layout with you, so you kind of like doesn't have to sit and draw all the holes here, and then you can of course manufacture your own PCB and then plug it in. So that's also fine. We're releasing that under there's a kind of like a license code where we're releasing it on Creative Commons license. We're releasing that on. The software is MIT, so that's completely free. So that's the option for that. And then there's a CO2 sensor. So that's this sensor here. It's actually a 1.8 volt sensor. So you can see on this sensor here that we have like a voltage regulator and level shift and things like that. So one doesn't have to be concerned about that. So that's a CO2 sensor. So it's actually a TVO sensor, so total volatile organic compounds, and that calculates a CO2 estimate. But volatile, it could be anything. So this is, of course, one of those that's meant for air conditioning at home or something like that to figure out if it's time to open a window or not. But hey, you can put it in a rocket, and then if you're kind of like guessing what kind of other volatiles that should be flowing around there, then you use that to pick up that, and you kind of like use that for calculate. You can use the data sheet to kind of like see what else it can pick up. It's a SGP 30 from Sensitron, I think it's called. So that's what we're using here. I also just want to give one little warning that, for example, the weather sensor. Right now, the weather sensor here is a SAT 3X, but this is like the third weather sensor we do, because from time to time we have an issue with that suddenly the sensor is not available. Okay, you probably heard about chip shortage even in the US. So when we do that, we simply just use another sensor that gives the same information, and we update the software so it can handle multiple different sensors. So we only had the issue with the weather sensor, and then the accelerometer is using a new sensor compared to an older prototype, but that was never released. So there's actually only one out there like that. We don't have, and this is maybe a good idea for a sensor if you want to do it, we only have the accelerometer as an IMU. There's no gyroscope, there's no magnometer. So if you want to take for example, NSM 9DS1 from Adafruit or SparkFun or something like that. They have like nice small breakout boards. Then that's ideal to maybe plug into this thing here, and then you have a whole gyroscope and 9 degrees of freedom kind of like calculation you can do. So that's an example of expansion you can do. We found that when we run this experiment earlier, people are only interested in the accelerometer. So we want to kind of like make sure that it's low enough price that it's accessible for everyone. So a 9DS1 is like a more expensive chip than what we use here as an accelerometer. Questions? So just William, while people think about a question, you're asking about what ESP it is. No, it's not one of the new ones. So it's not a S2 or anything like that. One of the reasons why I'm using the old one is because, for example, the SX doesn't support CAN. So the old one have CAN, it's a dual core, it's a low power and things like that. But I'm experimenting with a C core instead, because that have direct USB interface direct on the chip, similar to some of the SAMD thing have. It doesn't have CAN, so it's not for that purpose. But the idea is that they can actually run the same software. So it might be that we're doing that as an easier way to program these cores in the future. But for now, it's a standard ESP32, not the SX, not the S2 or 3, and not the C2 or 3, and not the upcoming 8s. We're not using any of those. And it's dual core, which might not be super necessary for a lot of the software, but if you do some machine learning or a lot of interrupt stuff and that kind of stuff, then it's nice. And of course, it also have a low power core, so you can kind of like really sleep, and if you have other projects where you want to not really do a lot, but rather have it running battery for a long time, you can do that with the same core. Yeah, Judy, I think that's it. I think if it was only meant to be an hour, then we are 12 minutes over time. So maybe this is a good time to, I think, Judy, we're gonna do the same as last time, just hang around until everybody have logged out if there's a question before we fall over.
Cody, over to you.
Yeah, I mean, I think if nobody has any further outstanding questions at this exact moment, then we might wrap it up. But of course, though, please join that Discord channel too. If you have a question, feel free to drop it in there, or hang on to it till the next session if it's not absolutely pressing. If you have any questions about shipment status for your kits or anything, please reach out to us directly at one of our emails, either to me or Judy. I believe you guys should have that, but I can throw our emails in the chat again real quick. But yeah, I mean, if that's it for everybody else, then I think we could definitely let you guys go. And we'll make sure that you guys have access to this video too. So if there's any information that you may have missed in the moment, you can definitely go back to it and watch it over again. I'm just checking the chat out, make sure we don't have anything outstanding that we forgot about earlier or anything. And I think we touched on everything. So I think with that, we'll probably wrap it up. I appreciate you guys all stopping by though. Again, one more time, I'm going to say it 1,000,001 times. Please join that Discord channel, though. That's going to be like the center hub for all communication between students, teachers, everybody, right? And that's the best place too, because we can share content to you guys directly through links and whatnot. And there's always somebody who seems to be up and at it in that Discord channel at all times. I seem to get a notification every hour or so, depending on the time. So there's definitely going to be somebody available who could probably help you out a little bit. If that's all, then I will say have a good night, everybody. And I'll see you in the next one.
Thanks.
Thank you so much.
You all.
Thanks,
Thank you all.
everybody. Bye.
Thanks.
Thanks, everyone. Bye.